All right, guys, Mr. Antonucci here, and in this third video, we're going to talk about performing a one-sample t-test for a mean. And so this is the appropriate inference procedure for testing a claim about a population mean. We call it a one-sample t-test for a mean. And as you can see here by the definition, one sample t-test for a mean is a significance test of the null hypothesis that a population mean is equal to a specified value when the population standard deviation is unknown. So again, as always, whenever you perform a significance test in general, but specifically here about a population mean, you want to make sure you follow the four-step process that we've been outlining throughout the course here. So here's an example. The level of dissolved oxygen, or DO, in a stream river is an important indicator of the water's ability to support life. A researcher measures the DO level at 15 randomly chosen locations along a stream. Here's the results in milliliters, milligrams per liter, or mg over L. An average dissolved oxygen level less than 5 milligrams per liter puts aquatic life at risk. So we're going to have two parts to this question. First one, do the data provide convincing evidence at the 0.05 significance level that aquatic life in this stream is at risk? Then we're going to talk about type 1 and type 2 errors. The important thing with this is when we are asked to provide convincing evidence given a significance level, this is a big hint that we need to use the four-step process. So we're going to start here with the state step. We need to state our null and alternative hypothesis along with the parameter and the significance level. So we have our null where the mean is 5 and the alternative where the mean is less than 5. And we know this is a one-sided test for less than because it says an average dissolved oxygen level less than 5. Okay, so it's a one-sided test where mu equals the mean dissolved oxygen DO level in the stream using significance level 0.05. That's all we have to do for the state step, but make sure you complete all four aspects of that: the null, alternative, the parameter defined in context of the problem, as well as the significance level being the fourth thing. Then the next thing we want to do is our plan step, and this is where we state the inference procedure we're going to use and check the conditions. So let's do that now. This is a one sample t-test for a mean. Okay, so we write one sample t-test for a mean. And then we begin to check the conditions. The normal large sample condition is satisfied because the sample size, well, it's not satisfied actually. I misspoke there. The sample size is small because it's 15, which is less than 30. So we have to draw a histogram here. And if we have a histogram of the situation, we can see that it's roughly symmetric, shows no outliers or strong skewness. Also want to mention that we also put the random and 10% condition in here. So again, you can't just put random 10% normal large sample and put a check mark. If you're checking the random condition, you have to state that, in this case, the researchers measured the DO level at 15 randomly chosen locations. 10%, 15 is less than 10% of infinitely many possible locations along the stream. Also, for the normal large sample condition, if the sample size is less than 30, remember, you have to draw a display of the data to analyze it, unless you know that the population distribution is approximately normal, which they didn't state that here, so we don't know that. The next step we want to do is the do step. This is where we perform our calculations. So the mean and standard deviation of the sample are listed as well as the sample size. It's important to write that information down, and you can do that by plugging this information, the data, into your calculator and doing one variable statistics, summary statistics on that. Then we get the t-star critical value of negative 0.944. Remember, we do our sample mean minus the hypothesized mean divided by the standard error of the sample. Okay. And then this gives us 14 degrees of freedom, because 15 minus 1 is 14, and the t-star value of negative 0.944, which results in a p-value of 0.1809. That's with 14 degrees of freedom. So if you use technology, that's what you would get. If you use the table, this particular t-value of negative 0.944 is not on the t-value, but on the line with 14 degrees of freedom, the t-star critical value negative 0.944 is going to be between 0.15 and 0.20. So that's the range of probabilities from the t-table. Okay. And that makes sense with our calculator value because 0.1809 is between 15 and 20. Okay, so we produce a graph here of, let me just make this a little bit bigger, of the t distribution with 14 degrees of freedom. See the t-star critical value right here is almost at -1. This area corresponds to the probability of getting a result this extreme or more extreme if the true mean DO level is 5. Okay, so we want to write our conclusion. Because p-value of 0.18 is greater than our significance level, we fail to reject the null. We don't have convincing evidence that the true mean DO level in the stream is less than 5 milligrams per liter. Okay, so that's the complete 4-step process there. Next thing we had to do was answer the question, given our conclusion, what kind of error could you have made, a type 1 or type 2 error? Explain what the error would mean in context. Well, since we failed to reject the null, we could have made a type 2 error. In other words, failing to reject the null when the alternative is true. If we did, then the true mean dissolved oxygen level in the stream is less than 5 milligrams per liter, but we didn't find convincing evidence with our significance test. That would imply that aquatic life in the stream is actually at risk, but we weren't able to detect that fact. Now, quick point about this is that to reduce the chance or likelihood of making a type 2 error, the researchers in this example could have taken a larger random sample of stream locations. And doing that would yield a more precise estimate of the stream's true mean dissolved oxygen level. So in other words, the larger the sample size, that's going to increase the power of the test to detect if the alternative is true. Another way to increase the power of the test would be to use a higher significance level like 0.10, and that would make it easier to reject the null where the mean is 5 when the average DO level is less than 5 milligrams per liter. But again, increasing the significance level also increases the probability of making a type 1 error, which is finding convincing evidence that the stream is healthy when it actually isn't. And that probability is equal to the significance level. So the probability of a type 1 error would actually increase from 0.05 or 5% to 0.1 or 10%. So just a quick AP exam tip as we wrap up here. You can use your calculator to carry out the mechanics of the significance test. But again, we said this before, there's a risk involved. If you give the calculator answer but don't show your work and one or more of your values are incorrect, you will likely not get any credit for the do step. So make sure you include the test statistic, degrees of freedom, and p-value in the do step, along with the elements of the remaining 3 steps, like the state, the plan, and the conclude. All right, guys, hope that was helpful to you. Reach out if you have any questions. Take care.